Okay, math analysis students, this is a recording for the section 9.1 homework, the worksheet on proving trig identities. I'm going to do problems 6, 8, and 9. I think 1 through 5 are pretty fast problems. They only take a couple steps, mainly just converting into sine and cosine, and then reduce down if you can. These ones where it starts to get a little tricky. Number 6, actually, though, is not terribly difficult. If I can get my pen to work well. Let's see here. Well, maybe not. Let's go, pen. There we go. Okay. So on number 6 here, again, I'm going to work with the more complicated side and try to boil it down to the simpler side. You might be tempted to convert this into 1 over sine. So turn the cosecant into 1 over sine and then multiply it in, just distribute it in. That turns out, at least from what I saw, to pretty much be a dead end. So we're going to ignore that and try something different here. I mentioned this in class. When you see ones flying around, when you see ones and something squared flying around, start thinking Pythagorean possibly. Remember the base Pythagorean identity, the parent one, is sine squared plus cosine squared equals 1. Well, can I somehow manipulate that to where I have 1 minus cosine squared on one side? Well, it turns out I can. If I just minus cos squared from both sides, this really all becomes just sine squared equals 1 minus cosine squared. So what that means is I can substitute, instead of 1 minus cosine squared, there it is, 1 minus cosine squared, same thing, I can replace that with just sine squared. So this whole thing actually just becomes sine squared of x. Remember, I sometimes just forget to write that x, so don't think that it's something magical, something new. It's just Mr. G forgets sometimes. So I converted that into sine squared. Now if I turn this into just 1 over sine squared, 1 over sine, well, now you just have sine squared on top, 1 sine on bottom. That will cancel with one of those, and lo and behold, you're just left with sine x, which is exactly what we wanted. That one actually is pretty fast, just maybe what, 2 steps there. Once you recognize that there's, oh, that's a Pythagorean identity, just kind of written in a different way. So again, the main thing was I replaced the 1 minus cosine squared. See if I can get this all the way over here. There we go. The 1 minus cosine squared was sine squared. Number 8 is a little more difficult looking. How the heck does secant squared minus cosecant end up being tangent squared minus cotangent? This one, I decided to work on the left side, and this is definitely a tricky one. This is why I decided to put on here. I've tried converting this into 1 over cosine squared and 1 over sine squared here, and putting them together, and I just ended up at dead ends. So maybe you can find a way to do it that way, but I actually did eventually see that there was a fairly short method. And this is definitely a tricky one, and here's what I was thinking. I have secant squared here. In the end, I need tangent squared. Is there some link between secant squared and tangent squared? Well, it turns out there is. We had another Pythagorean identity that said, excuse me, let me rewrite that. I should write it in order that I did it in class. We had one that said, what was it? Tangent squared plus 1 is secant squared. So I can really just replace secant squared with 1 plus tangent squared. It's equivalent. So I'm just going to substitute in for secant squared tangent squared plus 1. Now, is there a link between cosecant and cotangent? Yeah. There's another Pythagorean identity that said 1 plus cotangent squared was cosecant squared. And when I was learning this, I was wondering, is there really a reason why the one's second, and then down here the one is first? The only reason is because, as I showed in class, the way to actually get the blue and the green ones there is if you divide everything by cosine squared, you get this. If you divide everything by sine squared, you get this. It just turns out that you get a 1 there when you do the division. The 1 goes there. So again, all of that basically was just, that confused me in high school. I'm not sure why. Why is the 1 there? Why is the 1 there? It doesn't matter because it's addition anyway. Okay, so back to the problem at hand. Secant squared is, I'm sorry, cosecant squared is actually 1 plus cotangent squared. So I can replace that with 1 plus cotangent squared. Now remember, it's minus this, so it's minus the whole thing. So you've really got to think, oh, I'm making that negative, and I'm making that negative. And then it's just going to fall right out from there. So the front is still just tangent squared of x plus 1. This now became minus 1 minus cotangent squared. And lo and behold, the plus 1 minus 1 in the middle go away. See ya. And there we go. We're left with tangent squared of x minus cotangent squared of x. And we're done. That's what we wanted. Again, that one doesn't really follow the convention of turn everything into sines and cosines. It's a little more difficult one, but again, how did I know to do that? Well, I noticed that, well, I have a secant squared, I need a tangent squared. There's a link. I had a cosecant squared, I needed a cotangent squared. There's a link between them. And it turned out it just boiled right down. Okay, one more that I'm going to do, number 9. This one, I think when you look at it just at face value, if you just take a step back, it looks bizarre. Adding these two is the same as multiplying them, which is bizarre. That's not a normal thing. But it definitely actually does turn out. We mentioned this in class. When you have stuff that's separated, and then over here it's combined, I've found, just in my experience, that it's easier to try to combine these so that I have one thing, because this is just linked together with multiplication. These are separated from each other with addition. So I'm going to try to combine these. And this is one where the only thing I could think of was go to sines and cosines. So secant squared is 1 over cosine squared. I don't know why I'm writing an angle. Cosecant squared is 1 over sine squared. Now again, they're still separated here. Over here, they're not separated. They're linked together. So I should probably be adding these together and actually get one thing. Well, I need common denominators. The common denominator would be cos squared, sin squared. I would need both of those. So really the first fraction is missing the sin squared. The second fraction is missing the cos squared. So now if I were to multiply that and add the numerators, the numerator here would be, on the left side of the sine squared, obviously sine squared times 1, plus, over here, 1 times cosine squared, just cosine squared. All over the common denominator of sine squared, cosine squared, on both sides, sine squared, cosine squared. Okay, well, how does that get us closer? Well, actually, up here, trigger should be going off, hopefully. that is a big deal. Sine squared plus cosine squared, that's our base, our parent Pythagorean identity. That just equals 1. All that yellow stuff is just 1. And actually now I'm actually very close to the end. These are on the bottom of the fraction. If I were to try to flip them up, it'd be doing the reciprocal. When I flip sine squared up, it is secant squared. Oh, excuse me. It's cosecant squared. Nope, not cosine. I'll do that again. When I flip sine squared up, it is cosecant squared. When I flip cosine squared up, it is secant squared. Which, obviously, we know that it doesn't matter what order since we're multiplying. We're done. So that was one of the more classic ones where I decided to write them in terms of sines and cosines. Right there and right there in the black. I decided since it's combined over here, I should probably actually try to combine these, meaning add the fractions. That required common denominators. When I did that, the numerator just became sine squared plus cosine squared, which is just the number 1. And then finally, sine squared, if that's on the bottom and I bring it up, it's secant squared. Cosine squared, if I bring it up, it's, oh wait, I said it wrong again. Sine squared is cosecant squared. Cosine squared is secant squared. But either way, you're good. So hopefully this helps a little bit with a few of those proof problems.